All right, what's going on? This is ECE 20002, and this is spring 2021 exam number 2. And I am re-recording the intro because the first one was funny, but a little bit unnecessary. So anyways, with that, let's get started. Okay, question 1. The switch in the circuit below switches from a 3-volt source to a 15-volt source at time t is equal to 0. Find V sub c of t for times t greater than or equal to 0. Okay, so what we have here in this question is we have a time-switched RC circuit. And so what the problem has given us is we have this circuit down here that has 2 resistors and a capacitor, and those elements are initially attached to a 3-volt source. And at time t is equal to 0, that 3-volt source switches to a 15-volt source. So this little thing here at t is equal to 0, then goes over here, and this 3-volt source is now a 15-volt source. And that is the only change that occurs within the circuit. And so what the question is asking us to find here is it wants us to find V sub c of t for times t greater than or equal to 0, which of course is just the voltage across this capacitor as a function of time after the switch has occurred at time t is equal to 0. So in order to get that answer, we are going to apply the capacitor voltage equation for an RC circuit after the switch has occurred. And so if you remember back to 2K1, for an RC circuit, the voltage across a capacitor, V sub c of t, the thing that we are trying to solve for, is going to be equal to V sub c of infinity plus V sub c of 0 from the negative limit minus V sub c of infinity times e to the negative t minus t naught, with t naught being our time of excitation divided by tau, tau being our time constant, which for an RC circuit is equal to our equivalent resistance times our equivalent capacitance. And so all that we need to do to answer this question is solve that equation that I just wrote. And to do that, we need to find 3 things that we don't already have. So the first thing we need to find is V sub c of infinity. The second thing we need to find is V sub c of 0, our initial conditions of the voltage on our capacitor as the switch occurs. And then lastly, we need to find REQ so that we can solve for our time constant for this particular circuit. And so once we find those 3 things that I just wrote, V sub c of infinity, V sub c of 0 from the negative limit, and REQ, we can plug those values into our capacitor equation that I wrote up top, and that will provide us with our answer. So let's get into it. The first thing is V sub c of infinity. And remember that this question is asking us to find the voltage across the capacitor at times t greater than or equal to 0. So in this circuit, after the switch has occurred, we want to find the voltage across this capacitor. And so let's go ahead and rewrite what this circuit looks like after our switch has occurred with this 15-volt source attached, right? So to just make it look a little nicer, 15 volts, got our 1 ohm to our 2 ohm. Sorry, I don't know what the right way to write a circuit is, but as long as you get there, eventually it's fine. All right, so now what we want to do is we want to model how this circuit that I just wrote, right, the circuit after the switch has occurred behaves at t is equal to infinity. That way we can find V sub c of infinity. And so because we have a 15-volt DC source attached, we know that this capacitor will ultimately be fully charged by this DC source here. And so it will ultimately become an open because current will stop flowing through the capacitor. And so as time goes to infinity, this capacitor becomes an open. So at t is equal to infinity, we can write how this circuit will look and behave like this. We have our 2 resistors still. And then this capacitor, because it is fully charged, is now just an open circuit. And that is what V sub c of infinity is. And so with that, in order to now find V sub c of infinity, all that we need to do, oh no, that's going to cause me problems. Why did I do low power? Sorry, back to that. Okay, so with that, in order to now find V sub c of infinity, all we need to do is find the voltage across this parallel 2 ohm resistor here, right? So they share the same top nodes, they're in parallel. So the voltage across that 2 ohm resistor will be equal to V sub c of infinity. And since our capacitor is now just an open circuit with no current flowing through it, we can just do voltage division on these 2 resistors here in series with our 15-volt voltage source. And so in order to do that, remember, voltage division is just a shortcut from creating a KVL expression within a series resistor circuit, which is what we have now with our capacitor being an open. And so just as a reminder of how we do that, you take the resistor that you want to find the voltage across, you divide it by the sum of the resistors, and you multiply it by your source. And so in this scenario, we want this 2 ohm here. So 2 divided by our sum, 2 plus 1, times our voltage source, 15. So that's going to be 2 over 2 plus 1. 2 plus 1 is 3. So that's 2/3 times 15. 15 times 2 is 30, divided by 3, 10 volts. Okay, right? So because, just to review how we found this value is going to be equal to V sub c of infinity, because we know that when you apply a DC source to a capacitor, it ultimately becomes an open where no current flows through it. With that, we then turn this circuit in here at infinity into one where current only flows through those resistors here. And so therefore, we can perform voltage division on that in order to find the voltage. No, okay, sorry. So in order to perform voltage division here, because we know that the voltage across that resistor will be equal to the voltage across this capacitor, and so we can just do voltage division. That's what we did. Enough said. V sub c of infinity, 10 volts. So next what we need to find is V sub c of 0 from the negative limit. And so that is our initial voltage conditions on our capacitor down here, at the time of the switch. And we can recognize that the initial conditions on the capacitor down here will be equal to the final conditions on the capacitor up here before the switch has occurred. And that will be equal to the final conditions because, right, this 3-volt DC source here, as we are assuming, has been activated, since the dawn of the age, right, since negative infinity. And so therefore, this capacitor over here is fully charged as much as it can be by this 3-volt source. And so meaning it is behaving like an open, and thus, in order to find V sub c of infinity, we can perform the same method to find in order to find V sub c of 0, we can apply the same method that we used in order to find V sub c of infinity on the circuit before the switch. So let's go ahead and rewrite the circuit before the switch real quick. It's the same exact thing, except we now have a 3-volt source instead of a 15-volt source. And so, right, this capacitor is going to behave like an open as the transient charging phase wore off whenever this circuit was on in 1960 or something. And so it just then is going to become an open. Right, we have our resistors, but they're now with this 3-volt source. And so we're going to perform voltage division again. But it's going to be 2 divided by 2 plus 1 times a 3-volt source now. So 3 times 2 divided by 2 plus 1, that's 3. That's 2 volts, right? And so, enough said. V sub c of 0, our initial condition on the capacitor at the time of the switch is equal to essentially the final condition of this first circuit when we have the 3-volt source attached, right? The circuit before the switch has occurred. And so we're going to apply the same methodology where the capacitor is going to be as short once it's fully charged. We can perform voltage division on these resistors in order to find what the voltage across the capacitor is at V sub c of 0. And it's 2 volts. Okay, so there we go. And the last thing that we need to do is we need to find our equivalent resistance such that we can find our time constant. And so if you remember, to find Req, you simply need to short your voltage sources, right? So let's take this circuit here, just find the equivalent resistance. So we short our voltage sources. And so with that, this 1 ohm resistor is now in parallel with this 2 ohm resistor. And then we have this capacitor over here, but this capacitor is ideal, and therefore it is purely reactive. And so our equivalent resistance will be given solely by the parallel combination of these two resistors. Right, they're in parallel because they share this top node and they share this bottom node. And so Req will be equal to the 2 ohm in parallel with the 1 ohm. And now if you remember, Req of 2 parallel resistors is equal to the product of the 2 divided by the sum of the 2. So it's just 2 times 1 over 2 plus 1. Big math, that's 2/3. 2/3 ohms, and so the equivalent resistance in this circuit is 2/3 ohms. And so from there, let's just go ahead and find our time constant here. So remember, The time constant for an RC circuit is RC. I personally always remember the time constant for an RC circuit is RC because there's this crazy old dude that I know that says or used to say a lot of crazy out-of-pocket things, and he is now super dead, but I will always remember him. And so his name was RC circuit, RC time constant. I don't know if that's helpful to anybody. If anyone has a better way to remember the RC time constant, which I'm sure somebody has to, please let me know. But until then, I will remember time constant is equal to RC because crazy dead dude. So REQ is 2/3. Our capacitor here, when we have 1, is 3.5 farads. And so likewise, our time constant is equal to REQ times CEQ. 2/3 ohms times 3.5 farads. That's 1. Cool. Tau is equal to 1. And so now that we have these values, right, we have V sub c of infinity, V sub c of 0, and our time constant. Let's plug it into this equation that we have, and we will be done. So V sub c of infinity is 10 plus 2 minus 10 times e to the negative t minus t naught, our time of excitation, which in this case is 0, minus 0 divided by our time constant, which is 1. We can simplify this further, and it is 10 minus 8 e to the negative t. And there we go. That is our answer. That is V sub c of t for times t greater than or equal to 0 within this circuit after the switch has occurred. And if we go down to our answer choices, our answer is right here. And there we go. That is correct. And so just as a refresher of how we did this, right, we have this, it wants us to ask, it asked us what the voltage across this capacitor is as a function of time. And so we use this equation here, which is the equation for the voltage across a capacitor. And if you don't remember how we got that, we get it by solving for the first order differential equation by using the IV characteristics of a capacitor. And you are welcome to go ahead and solve problems like that this way. You can do source transforms, get a Thevenin equivalent, set up a KVL expression, and do it that way. But what you should do is you should remember this equation like your life depends on it, and then you will make this question much easier to solve. From that, all we need to do is find the unknown values. We found V sub c of infinity by modeling how the circuit will behave after the switch occurs, by knowing our basic DC characteristics of a capacitor, and then we did voltage division because no current was flowing through the capacitor at time is equal to infinity. To find V sub c of 0, it was the same method except for we applied it to before the switch occurred, as the final conditions of the circuit before the switch occurred gave us the initial conditions of the circuit. After the switch occurred, we got that, and then we just solved for the equivalent resistance of our circuit by shorting our voltage source, and then we had two parallel resistors, combined them, found our time constant, plugged it back in, and we got the answer is 10 minus 8e to the negative t. And so there you go. That's how you do it, sort of. I hope that makes sense. I don't know, but good deal. Question 2. Given that f of t is equal to t of u of t minus 1 and g of t is equal to the direct delta function of t minus 1, compute f of t convolved with g of t at t is equal to 2.5. Hint, f of t convolved with g of t is equal to the improper integral from negative infinity to infinity of f of tau multiplied by g of t minus tau d tau. Okay, what we have here is a continuous convolution question. And what they have given us here is we have two functions, f of t and g of t, and they want us to convolve these two functions together and then find out what the resulting function of their convolution is equal to when the independent variable t is equal to 2.5. And so they have given us the convolution integral, and so we are going to plug in our values of f of t and g of t into that integral and then solve when t is equal to 2.5, and that's it. So just going to rewrite this. F of t convolved with g of t, what we are trying to do is equal to the improper integral from negative infinity to infinity of f of tau, which is just f of t plotted on the tau axis with tau replacing t, and that is multiplied by g of t manipulated into g of t minus tau, right? So we flip g of t on the tau axis, and then we introduce this dummy variable t, and that dummy variable t is representative of the improper integral, is representative of the independent variable within the resulting function y of t, right? So as we vary t within the resulting function, what occurs is that we shift this function g of t minus tau further down the tau axis, right? So as t increases, we shift g of t minus tau down the tau axis. And then we are going to integrate the product of these two functions with respect to tau. And so what this integral accomplishes is that for each specific value of t within the resulting function, we are going to return a value for each specific value of t that is equal to the resulting multiplication of these two functions when t is at a set value, right? And so that means that f of tau is plotted on the tau axis, and it is still. And when we set t to a specific value, it will also set g of t minus tau to a specific value, right? But it will just be shifted by whatever value of t that is, right? So if we had, g of 1 minus tau, right? That's just a still shifted function. And then what we're going to do is we're going to integrate the multiplication of those two functions over each other. And so for each value of t, what we get is a resulting value of this integral that tells us how much those two functions overlap. And so what we're trying to do is find out how much these two functions overlap in this way that we've manipulated them at t is equal to 2.5. So let's go ahead and plug in our values and then solve for t is equal to 2.5. So the improper integral from negative infinity of f of tau, which is just tau of u of tau minus 1, right? We just replace our t values with tau. And this is going to be multiplied by g of t minus tau. And we're just going to replace our t values with t minus tau. So this is going to be the Dirac delta function of t minus tau minus 1 integrated with respect to tau. And so right off the bat, the first thing that I see is that we have this unit step function here. And this unit step function is going to only return a value of 1 when tau is greater than or equal to 1. Otherwise, it is going to be 0 if tau is less than 1. And so with that, we have to restrict our bounds of integration, right? Because when this is 0, this entire expression is 0. And so there's nothing to integrate over. So we are going to integrate from 1 to infinity now, and we can get rid of that unit step function because it is just equal to 1. So now we have tau times the Dirac delta function, and I'm going to rewrite this expression here as t minus 1 minus tau. And the reason I'm doing that is that just as a reminder of what this Dirac delta function is, right? The Dirac delta function is equal to infinity within continuous time when t is equal to 0, and it is 0 for all other times. And so therefore, the only time that this Dirac delta function will return any value is when this inner value is equal to 0. And so therefore, t minus 1 minus tau has to equal 0, and so t minus 1 is equal to tau. And so with that, we are then going to restrict our integration bounds again because this function only returns a value when t minus 1 is equal to tau. And so that then becomes t minus 1 from the negative limit to t minus 1 from the positive limit. And we have tau times the Dirac delta function of t minus 1 minus tau d tau. Now, to solve this integral, we are now going to have to plug in our specific value of t. So, right, we declared that t minus 1, t minus 1 is equal to tau. And as the question has specified, we have a t value of 2.5. So t is equal to 2.5, and tau is equal to t minus 1, and so therefore it is equal to 2.5 minus 1, which is 1.5. And so we can plug in this value of tau into this variable here, and what we get then is 1.5, and we can take that out of the integral, and then we have this multiplied by t minus 1 minus tau d tau. And now that we have set tau to equal to 1.5, we know that this inner function will return 1 of 0. So then what is the integral of a Dirac delta function? Well, a Dirac delta function, as I stated earlier, is equal to infinity when t is equal to 0. And so it is just a giant signal at 0 with infinite height and infinitesimally, I don't know, that weird one word where it's like super skinny, or like it's like 0. It's like tangent, but like it's infinitesimal. The width is basically 0. Okay, that's what I'm trying to say. And so this has no width, but when we integrate the Dirac delta function we actually get the area is equal to 1. Why that's the case, I don't know. I actually haven't looked at the proof. I think I've looked at the proof, but I don't remember why it is. You can look that up, but it's not really important. All I know is that if we integrate across this, the area is equal to 1. And so therefore, the area of this with respect to integral is equal to 1. And so this is just equal to 1.5 times 1, which is just equal to 1.5. And so therefore, this is our answer of the convolution of f of t and g of t when t is equal to 2.5. All right, sorry for going off the wheels there at the end. So let's review what we did. So this question gave us two functions, right? F of t and g of t. And they wanted us to convolve these two functions together and then find out what the result of that convolution is when the independent variable t is equal to 2.5. And so we performed the convolution integral here. We plugged in our values, restricted our bounds, and what we got was this. And we had this Dirac delta function, and if you remember, the Dirac delta function is equal to infinity at t is equal to 0 and 0 for all other times. So then we restricted our bounds further, and then we finally plugged in our value of t is equal to 2.5, which then sets tau to be equal to 1.5, since t minus 1 minus tau has to be equal to 0. So therefore, tau here has to equal to 1.5. We took that value out just as a constant, and then we performed this integral. And remember, if we're integrating across a Dirac delta function, it's equal to 1. It just is. I don't know. I don't know actually why that is. Maybe I'll have to figure that out. But regardless, that's just what it is, and so it equals 1. 1.5 times 1 equals 1.5, and that's how we solved it. I think that's an okay enough explanation. Probably like a 6 out of 10, but I think it should suffice for this question. So yeah, there you go. Okay, question 3. Given f of n is equal to 5, 3, 2, 1, and g of n is equal to 1, 2, 3, compute f of n convolved with g of n for n is equal to 4. Hint, f of n convolved with g of n is equal to the infinite sum from m is equal to negative infinity to infinity of f of m times g of n minus m. Furthermore, function definitions start at 0, i.e. f of 0 is equal to 5 and g of 0 is equal to 2. Okay, what we have here in this question is a discrete convolution question. And so what they have given us is two functions, f of n and g of n. And they want us to convolve these two functions and then find what the value of those two functions convolved is when the independent variable of the resulting function, n, is equal to 4. And so they have given us the definition of what discrete convolution is. And so I'm just going to go ahead and write that out. Right? We're going to convolve f of n with g of n. And we are going to then set n to a specific value of 4, and we will have our answer. And so this is equal to the infinite sum from m is equal to negative infinity to infinity of f of m, right? So what we're doing here is we take f of n, and we just plot it straight on this new axis, m, right? With m replacing n. So it's going to be the exact same, just we have m instead of n. And then we're going to multiply it by g of n manipulated into g of n minus m. So first what we're going to do is we're going to flip that function of g of n on the m-axis. So it now becomes negative n. And then we are going to add this dummy variable n, which is representative of the independent variable of the resulting function of this convolution. And so what that value of n does is it shifts g of n, right? So if n is 0, right, it's just going to be g of negative m. If it's 1, it's 1 minus m, right? And so as n increases, it further shifts g of n minus m to the right down the m-axis. And so that's what that does. And so we are going to simply plug in our two functions into this summation here, and we will have our answer. And we're going to set n in this case specific to 4, right? So this is going to be f of m times g of 4 minus m. So it is going to be g of n flipped on the negative m-axis and then shifted to the right by 4 by our value of n is equal to 4. So let's go ahead and plot these two functions in order to visualize this better. So f of n on the m-axis, right, f of m, is going to be exactly as it looks on the n-axis, except for we are going to have m as our x-axis instead. So at 0, right, it is going to be 5. And then at 1, it will be 3, and then 2, and then 1, and that's it. And so that's what f of m is. And then what is g of 4 to the minus m? First, I want to visualize what g of negative m is, right? So this is This would be if we had an n value of 0. It's just g of negative m, which means we're taking g of n and we're just flipping it on the m axis. And so it's going to look something like this. At 0, we're going to have 1, but then we're going to go 2 at, is that right? Yeah, 1, 2, 3, 2 at negative 1, and then 3 at negative 2. And so, as we increment m up and upwards, it's going to shift this discrete time signal. So if we increment by 1, right, it's going to shift this signal, with this being 0, further down the axis. And so when we set our n value in this case equal to 4 minus m, this becomes 0 becomes here, and then we have 1, 2, 3, 4. And up here our values are 0, 1, 2, 3 as our m values. And so now what we're going to do is we're going to perform this summation. And the way that we perform the summation is essentially we are multiplying these two functions at their corresponding m values together, and then we are summing together those corresponding multiplications. And so to visualize that better, I'm just going to rewrite f of m down here. Starting at n is equal to 0, it is equal to 5, 3, 2, 1. And then I'm going to write g of 4 minus m. Starting at n equals 0 is 0, and then it's 0 again, and then it starts to go to 3, and then 2, and then 1 at 5. Ooh. Yeah, that's right, at 4. And so what we're going to do now is we're going to multiply these corresponding values together. So multiply, multiply, multiply. And then we're going to sum those corresponding multiplications together in order to get the result of this summation here. And so we will have 0 plus 0 plus 6 plus 3. No. Can't do math. Plus 2, and then there's no corresponding here. So, this would be representative of 0 plus 0. And so this equals 8. And so this is the answer to our question. The discrete convolution of f of n and g of n when n is equal to 4 is 8. And that is our answer. And so just to review what we did here, they gave us two functions, f of n and g of n, and they are discrete time signals that are very simple. They're just like a matrix of data or array of data. And so they wanted us to convolve these two functions and then find what the result was at n is equal to 4. And so ultimately, they gave us this discrete convolution integral or summation. And what we do is we take f of n and we plot it directly on this new m-axis. And it looks like this graph here. And then we take g of n and we flip it on the m-axis, right? And then we are going to introduce this n variable here in order to be able to shift that signal down the m-axis. And in this case, we had an n value of 4, so we shifted it. No, that's bad. Yeah, we shifted it g of 4 minus m, and that ultimately looked like this. And then all we did based on this summation here is we multiply the corresponding values together, and then we summed all those multiplications in order to get 8. And that's all that we did, right? And so what convolution is flip, slide, multiply, right? You flip g of n onto this new m-axis, and then you slide it with the variable of n, and then you multiply those corresponding values together. And ultimately, you will get a resulting function y of n. But in this case, we had a set n value, and so we did not slide our function continuously. We set it here on this axis, right, when n is equal to 4. And so we got a discrete value of a numerical value. But usually you will get a function of some kind. So in discrete convolution, right, you have some data set, right, like they gave us, with values, x1, x2, x3, x4. And what you do is you take the other function, right, say you have some function here like we did. And what you're going to do is you're going to flip it, right, you flip it. And then what you're going to do is as n increases, right, this is so when n is equal to 0 or something like that. No, that's not actually accurate. But what you do as n increments is you further slide this down, right? And then you take the multiplication of these values and you sum them all, and that's your convolution at that specific n value. And then you're going to slide it again as n increments again. And then you're going to take the multiplication of those overlapping values and then sum them. And then you're going to do it one more time, right, while they're still overlapped. You're going to take the multiplication of those, and there's only one value there, and then you continuously slide this function of g down the tau axis, and you multiply as you go about it. And in this case, we just set it at a specific value where n is equal to 4. And so we just took the summation of those overlapping values of multiplication. And so that's what discrete convolution is. It is the exact same as continuous convolution, except for we're shifting with discrete time signals, so n is an integer, and it's actually a little bit easier to visualize, right? We set f of n, we take g of n, we flip it onto this m-axis, and then we slide it. And then we slide it down again, and we slide it down again, and we take continuous multiplications at each point of their overlapping ranges, and that's what our convolution is equal to at each specific value of n, and that results in a function if you do it with respect to n, but we set n to 4, and that's how we solve this question. Sorry, that was not very concise, but that is how you do the problem. So there you go. Okay, question 4. The unit step response of an LTI system, i.e. the response to a unit step input, is y sub u of t, which is equal to e to the negative 4 u of t. Find the response y of t of the system to an input of x of t is equal to 3e to the negative t u of t. Hint, use that y of t is equal to x of t convolved with h of t. Okay, what we have here is an impulse response question. And so what they have given us is the unit step response of an LTI system. An LTI system stands for linear time invariant. So the system is both linear in that it obeys the laws of superposition and homogeneity in between the inputs and outputs. And it is also time invariant, meaning that if you time shift the input, the output will be time shifted in the same manner, which is not too important to our question, but nonetheless, it is important that it is an LTI system because every LTI system can be characterized by something called the impulse response, which we denote as h of t. And what's awesome, or what is the impulse response? Well, it is exactly what it sounds like. It is the response of an LTI system when we apply the impulse function to it, right? The Dirac delta function, that little thingy, weird thing that I wrote there, which is basically infinity at 0 and when t is equal to 0, and then 0 for all other times. And so when we apply the Dirac delta function to an LTI, the output of the system is equal to the impulse response. And so what's great about the impulse response is that if we apply any input to an LTI, if we convolve that input with the impulse response, we will get the resulting output of the LTI, right? And so, that's even true of the Dirac delta function, right? By the time shifting property, if we convolve anything with the impulse function, we get what we convolve with. And so with that, what this question is asking us to do is to find the response of the system y of t when we input x of t is equal to 3e to the negative t u of t into this function. And we're going to use that x of t convolved with our impulse response is going to be equal to that value. So in order to do that, first we need to solve for what our impulse response of this LTI system is. So how are we going to do that? Well, we are going to use the unit step response. So what the unit step response is that if you apply the unit step input, right, unit step function into this LTI system, you will get the unit step response, which in this case is equal to e to the negative 4t u of t. So how is this at all related to the impulse response? Well, u of t is equal to the derivative of u of t, is equal to the Dirac delta function, right? So the Dirac delta function is this crazy thing, this impulse at 0, and the unit step function is equal to this. And so the derivative of this gives this. And so with that, we can also know that, okay, so with that, we know that the derivative of the unit step response is going to be equal to the impulse response. And we're going to use this in order to find our impulse response, right? So the derivative of this here is going to be equal to our impulse response. And so our impulse response is equal to, by product rule, this is equal to negative 4 e to the negative 4t u of t plus the derivative of the unit step function, which as we declared earlier is the Dirac delta function, multiplied by e to the negative 4t. And so, just as a note here, this Dirac delta function only returns a value when t is equal to 0. And so when t is equal to 0 in this exponent term, it is e to the 0, which is equal to 1. And so we can just completely get rid of this term here. And this is what our impulse response of this system is. And we got that by taking the derivative of the unit step response. And so from here, what we're going to do is we are now going to convolve that impulse response with our input function in order to find the output of this LTI system, what this question is ultimately asking us to do. And just a reminder, if you don't remember what the convolution, or just to establish what the convolution integral is, it is the improper integral, right, when we convolve two functions from negative infinity to infinity of x of tau, right? So we take x of t and we plot it directly on the tau axis, just replacing t with tau. And we're going to multiply that with h of t minus tau, right? So we're going to flip h of t on the tau axis with that negative tau, and then we are going to add in this dummy variable t, which is representative of the independent variable within the resulting function, right, y of t. And so when we vary that t value within the resulting function, we slide the impulse response down the tau axis, right? And so then we are going to ultimately take this improper integral at every specific t value in order to find what the overlapping multiplication of the input and the impulse response function are in order to find what the output of our LTI system is. So let's go ahead and plug in our values of x of t and h of t into this integral, right? So x of t is equal to 3e to the negative t ut, and so that is going to become, we're just going to replace t values with tau, so oh, I messed up already. 3e negative tau u of tau. And then we're going to multiply this by our unit step function, our impulse response manipulated into h of t minus tau. So we're going to replace t minus tau with every t value down here. So we're going to have negative 4e to the negative 4 t minus tau u of t minus tau plus u of, or no, not u, Dirac delta function t minus tau, and then this is d tau. And so right off the bat, because we have addition in this impulse response term, we're actually going to have two integrals, right? So this first integral here is just going to be from negative infinity to infinity of 3e negative tau u of tau times negative 4e to the negative 4, and I'm going to expand this exponent out, negative 4 tau e to the 4 tau, negative 4t times e to the 4 tau times u of t minus tau. And then we're going to add the integral of this function with the Dirac delta function. And when you look at that, what this is we're convolving x of t with the Dirac delta function. And by the time shifting property, this is just going to return x of t, right? We went over that earlier when we were talking about if you input, the impulse response, you convolve the impulse function with it, you're going to get your impulse response, right? And so that time shifting property applies here in that this term is just going to return x of t. And so this term is just equal to 3e negative t u of t. And so all we have to do is solve for this first integral here. And so right off the bat, when I see these unit step functions, I know that they're going to limit our bounds. And the reason for that is that this u of t function is only going to be equal to 1, it's only going to be on when tau is greater than or equal to 0, and it's going to be 0 for all other times. So from negative infinity to 0, this entire term, this entire expression is going to be nulled by the fact that u of t tau is equal to 0. So lower bound goes to 0 by that unit step function. The second one is going to limit the upper bound because tau needs to be less than t in order for this unit step function to return a value. Otherwise, it's going to be 0. And so that will set our upper bounds to t. And so within these bounds from 0 to t, both these unit step functions are equal to 1. And so we can just get rid of them from our expression. So now we have 3e negative tau times negative 4e to the negative 4t e to the 4 tau d tau. And I'm going to remove the constants here, so negative 4e to the negative 4t, because we're integrating with respect to tau. That can go out, and 3 can go out too. And so we will have negative 12 integrated from 0 to t of e to the negative tau multiplied by e to the 4 tau d tau. We can combine these two exponents here since they're multiplied together. So it's going to be equal to 4 tau minus tau. That will be 3 tau. And then from here, I'm going to, I made a mistake. This needs to be negative 12e to the negative 4t. And so from here, I'm going to perform u sub to compute this integral. I'm not going to go over how you do that, but if you forgot, there's no shame. Just look it up on YouTube. It is very simple. Essentially, we're going to make u equal to 3 tau. And, well, I guess I'll just say I do it. U is equal to 3 tau, and then du is equal to 3d tau. So du over 3 is equal to d tau. We plug that in, essentially, and what we get for this integral is that negative 12e to the negative 4t multiplied, we're going to divide this by 3, multiplied by e to the 3 tau from 0 to t. And so then this is going to be equal to negative 4 e to the negative 4t times e to the 3t minus e to the 0, which is 1. And this is going to ultimately be equal to e to the negative 4 e to the negative t minus plus 4e to the negative 4t. And so this is what this integral is equal to. And then we also have this plus 3e to the negative t term, which is coming from this extra little direct delta function that we have that we multiply by our input within this convolution integral. And by the time shifting property, just returns the input. So when we do that, we now are going to add this 3e to the negative t term. And all of these are multiplied by the unit step function. Right, this first one because it's just our input, and then this one because our bounds are from 0 to t. In order to confirm that we are integrating up to positive time in this sense, right, up to t, that t is a positive value, we are going to multiply by the unit step function u of t in order to confirm that t is in fact a positive value. And so with that, this is our answer, and we're going to simplify it because these are like terms. So we will get 4e to the negative 4t u of t minus e to the negative t u of t. And this is our final answer for the output of a system, the LTI system described when the input is 3e to the negative t ut. So when we go over to our answer choices, our answer is right here. So that was a lot, so let's review what we did. So this question gave us the unit step response of an LTI system. An LTI system is a linear time invariant system, and every linear time invariant system can be characterized by something called the impulse response. The impulse response is the output of an LTI system when the input is an impulse function. And by this, if we convolve any input, right, x of t convolved with our impulse response, it will give us our output. And so we are going to use that principle in order to solve what the output of this system is based on the input that they gave us. But first we needed to find what the impulse response was. And so the way that we did that is because they gave us the unit step response, right, the response of a system when we applied a unit step signal, we know that because the derivative of a unit step function is equal to the impulse function, the derivative of a unit step response is equal to the impulse response. And so from there, we took the derivative of this, and I actually, the first time I tried to record this, I made a mistake, and I forgot to do product rule. And I would imagine most people that made mistakes on this question made this error, but you need to do product rule in this sense in order to get this function as our impulse response. And then what we're going to do is we convolved our input with our impulse response, denoted by the convolution integral right here. We plugged in our values, and what we did is this term times this first term became this integral, and we computed that, and then this input term times this direct delta function term is essentially applying the time shifting property to our input function, and so it just returns our input function. So we did u sub, and we got that the output of this integral was this, and then we added on this term here, we combined them, we simplified, and the answer for the output of this system when the input is 3e to the negative t is that. So there we go. Question 5. The convolution of two pulses f of t is equal to u of t plus 2 minus u of t minus 2 and g of t is equal to u of t plus 1 minus u of t minus 1 is shown in the bottom plot of the figure below. What is the value of a and b in the x and y axis tick marks? Okay, what we have here is a graphical convolution question. And so what this question has given us is it has given us two functions f of t and g of t. And f of t is represented here in this top left plot and is equal to u of t plus 2 minus u of t minus 2, meaning it has a height of 1 and a width of 4, and it is centered at 0. This function g of t, represented in the top right plot, is equal to u of t plus 1 minus u of t minus 1, and so it also has a height of 1, but it has a width of 2, and it is also centered at 0. And so what this question wants us to do is to find these values of a and b. And a and b are represented as the y-axis and x-axis value within this bottom plot down here, which is equal to the convolution of f of t and g of t, right? So it is equal to some function y of t, and y of t is equal to the convolution of f of t and g of t. We'll just write it out. And as a reminder, what convolution is it is equal to the improper integral from negative infinity to infinity of f of tau, which is f of t plotted directly on the tau axis with tau replacing t. and then that function is multiplied by g of t manipulated into g of t minus tau, right? So we flip g of t on the tau axis with this negative tau, and then we are going to add in this dummy variable t. And this dummy variable t is the independent variable within our resulting function, right? So it is equal to the x-axis on this plot here. And as this value of t varies within the resulting function on this graph here, what it does is it slides g of t minus tau down the tau axis. And so then what the value of y of t is equal to then is the improper integral with respect to tau of these two functions overlap, right? We multiply them together at every specific value of t, right? So at some specific value of t, when g of t minus tau is shifted, say it's, I don't know, shifted 4 minus tau or 3 minus tau, right? It is shifted and held in place on the tau axis. F of tau is held in place. And then we integrate from negative infinity to infinity of the overlapping multiplication of those two functions. And that is what our y-axis value is equal to in this graph, right? It is equal to the maximum value, or it is equal to the total area of overlap of f of tau and g of t minus tau with respect to a specific value of t. And so what that looks like graphically is that let's take this function f of t and plot it on the tau axis, right? Let's make it f of tau, right? And we can do that because tau has the same attributes as the t-axis, and so we'll do this right here. What we're going to do is we're going to take g of t and we're going to make it into g of t minus tau on the tau axis. And so what we do is we flip it on the tau axis, right? And because this is symmetrical, it is just plotted exactly as it is on the tau axis. And then we have this value of t, which, as we vary t, it is going to shift this function of g of t minus tau. So as t varies down here, we shift this function through, and as we're doing that at each specific value of t, right, we are taking the multiplication of these two functions over one another and then accumulating that area with that improper integral at that specific t value, right? And so we keep going down and we just take the area of this. And so on this plot down here, what this value of a is representative of is the maximum overlap of those two functions as t varies, right? So it is equal to the point at which g of t minus tau is totally consumed by, f of tau, right? Because they have the same height and they're basically the same functions, except for that g of t minus tau has a width of 2 instead of 4. The maximum area, the maximum return value of y of t is going to be equal to just the maximum overlap between these two functions, maximum area. And so that's going to be equal to just the area of g of t minus tau, right? When this is maximally overlapped, the total multiplication of these two is just going to be equal to the area of g of t, which is just 2 times 1, right, with the 2, height of 1. And so therefore, a is going to be equal to 2, right? So a is equal to the maximum area of overlap of these two functions as we slide g of t minus tau on the tau axis. And so that's going to be equal to this interval where, somewhere between here shifted up to this point, all of these, and that's represented by these t values. And so then therefore, in order to find b here is going to be equal to the value at which g of t minus tau is completely consumed by f of tau as we slide it down the tau axis. But if we were to increase t, right, this shift any more and slide it further down, we would no longer have maximal overlap. And that is seen as our y of t value decreasing as t increases past the point of b. And so b is equal to the time shift that causes g of t minus tau to be here, right? With these two right edges of the functions completely aligned, meaning if I were to increase this shift any more and shifted it further, there would now be area where there's no overlap of these two functions, and thus we would not result in returning the maximum area of overlap. And so all we need to do is find what value of t that causes this shift to make g of t minus tau look like this on the tau axis. Right, so what is this shift? Well, it's just equal to 1, right? We have our centered at 0, and now our center is centered at 1 because we are going from 2 to 0 with a width of 1, with a width of 2. And so b is equal to 1, right? B is equal to the value that shifts that function of g of t minus tau in order to get it where their two right edges are aligned, and that's going to be g of 1 minus tau. So that's how we found a and b. If we go to our answer choices, is it is right there. And so just to review what we did, we have two functions, f of t and g of t, and we are going to convolve them, and then it results in this function down here. And what they want us to solve for is this value a, which is the y-axis value of the resulting function of the convolution. And this value of a is equal to the maximum area of overlap of these two functions multiplied together. And that is just going to be equal to the total area of g of t, because it will be totally consumed as we slide it through in this section here, right? And so that's equal to 2, because it's just equal to the total area of g of t. And then b is going to be equal to the value of t that causes it to be totally shifted into this sense, where the functions are maximally overlapped, but if t were to be increased any more, it would cause them to not be overlapped. And so that's when their right edges are fully aligned, and that is when we have a shift of 1 to the right, indicating a value of 1, because this is g of 1 minus tau plotted on the tau axis. And so that's how we found b. I don't actually know if that made very much sense. I'll probably have to go back and watch it and see if it did. But yeah, convolution is pretty, these questions are pretty easy to solve, but convolution itself has some moving parts that can be a little difficult to explain on the fly. And they take a little bit of time to understand when you're first learning it. So I hope that made sense, but we'll see. Question 6. Find the Laplace transform of t minus 4 times e to the negative 4t of u of t, the unit step function, at s is equal to 1. Okay, so what we have here is we have a Laplace transform, and this is a pure math question. There is no electricity involved. And so what they have given us is this function of time here, and they want us to perform the Laplace transform on that function of time in order to convert it into the frequency domain, into the s domain. And then they want us to evaluate that Laplace transform at s is equal to 1. So what is a Laplace transform? Well, a Laplace transform, that poorly written squiggly L thingy of some function, takes a function of time and converts it into a function of s, with s being sigma plus j omega, right? This is into the frequency domain. And so this is performed by doing the improper integral from negative infinity to infinity of f of t multiplied by e to the negative st dt. Now the good news is we don't actually have to perform this stupid integral here on our function, and that's because we are engineers and we are not math majors, and so they have given us this glorious little lookup table. So all we need to do is get this function of time here in terms of one of these things, right? Some function of time here, and then this lookup table will tell us what that function is within s domain, within frequency domain, right? This is the Laplace transform. And so we just need to get into one of these terms over here on the far left, and then we will get the Laplace transform. Then we'll just plug in the value of s and we'll be done. So let's go ahead and do that. So if we take t minus 4 here, e to the negative 4t u of t, and we distribute that t minus 4 term, we're going to get t e to the negative 4t u of t minus 4e to the negative 4t u of t. And so then we're going to take the Laplace transform of this function here, and you'll notice right off the bat this term is in the form of te to the negative at u of t, with our a value being negative 4, and so therefore this is the Laplace transform. It's 1 over s plus a squared, with a being 4. And so there we go. Our next term here is negative 4e to the negative 4t u of t, and so it is in the form of this function right here, and so that just gives us 1 over s plus a, with our a value being 4 again, and then we have a coefficient of negative 4, so it's going to be negative 4 over s plus a, s plus 4, and there we go. There is our Laplace transform of that function, and then we're just going to plug in s is equal to 1, right? That's what the question is asking. When we do that, we get 1 over 1 plus 4 squared minus 4 over 1 plus 4, and that's 1/25 minus 4/5, which is 20/25. This is equal to negative 19/25. And we know that 1/25 is equal to 0.04. That times negative 19 is going to be equal to negative 0.76, right? So 20 times 4 is 80 minus 4, 76. So there we go. Very simple question, pretty straightforward. This is our answer right here. And so just to review what we did here, they wanted us to Laplace transform this function here and then plug in a value of s is equal to 1, right? A value at s is equal to 1. And so remember, a Laplace transform is just this stupid integral, but we don't have to do that integral because we have this lookup table. And so we got our function down here in terms of these two forms. We performed the Laplace transform. We got this. We plugged in s is equal to 1, performed algebra. There we go. If anyone is confused on how to use a lookup table, just remember that f of t to f of s is the Laplace transform. And so f of t, if we can get our function that they give us in terms of one of these things, then we can know that the Laplace transform of those functions is of this form. Pretty straightforward. They didn't give us this term when I took the class. And so if you're confused on how to do an exponent times t, know that a tu of t is some function of time. And then if you multiply it by an exponent, if you take some function, multiply it by an exponent, it's going to be frequency shifted. And so it would be 1 over s squared, right? But then we have a frequency shift because we have that exponent within time domain. And so this is just 1 over s plus a squared. And so that's another way to find it when you have a t value multiplied by an exponent. It's just a frequency shift within frequency domain. So that should cover all the fronts. I hope that makes sense. Okay, question 7. Find the inverse Laplace transform of 9 over s cubed plus 3s squared. Okay, we have a very easy inverse Laplace question. And so what the question has given us is some function of s, and they want us to inverse Laplace transform that function. And so just as a review on what Laplace is, say we have some function f of t, some function within the time domain. If we perform a Laplace transform on that function, we are going to get a function of s within the frequency domain, so some function of s. Now, in this question, they have given us that function of s right here. So we are within the frequency domain, and they want us to inverse Laplace transform, or no, not negative up there. They want us to inverse Laplace transform that f of s frequency function right here back into the time domain in terms of t. And so that's all that we're going to do here. In order to complete that, what we're going to do is first we're going to take this function and get it into something tangible, right? So we're going to get f of s into something that is represented in these terms here on the right-hand side. That way we can use this lookup table to very easily see what the inverse Laplace transform is of those terms. The way that we're going to do that is by performing partial fraction decomposition. When we perform that partial fraction decomposition and we get it f of s into terms that are easily recognizable, we can get it back into f of t, into whatever terms this thing might be. So let's go ahead and first perform that partial fraction decomposition. So 9 over s cubed plus 3s squared. First, what we need to do is we need to factor this as much as possible. And so I'm going to factor out that s squared from both of those terms, and we will get 9 over s squared, s times s, and then just s plus 3 will be left over. And so in order to perform partial fraction decomposition, if you have forgotten, is we take the factored out terms within our denominator, and we are going to create 3 separate terms. So we're going to have a, some unknown coefficient divided by our first term, s, plus b, some other unknown coefficient divided by our second term, which is also s. And because it has been repeated, in order to differentiate that term from the first term, we are going to square it. And then finally, we do the same thing for our last term, s plus 3. And so what we're going to do in order to solve for these a, b, and c values that are unknown is we're going to multiply these terms in the denominator through. So we're going to multiply our denominator through, or we're really just going to multiply our denominator on both sides in the numerator form. That way it will cancel over here on this left-hand side, and it will go through to this right-hand side. Then we are going to compare those values to our numerator and solve for a, b, and c. So let's go ahead and do that. And when we do that, we have a times s, s plus 3. One of those s's cancels, plus b, that s squared cancels completely, plus c, that s plus 3 term cancels completely. And when we simplify this, we get a times s squared plus 3s plus b times s plus 3 plus c s squared. And this is equal to our numerator 9. And so what we can do further is then we're going to say a plus c times s squared plus 3a plus b times s plus 3b times 1 is equal to 0s squared plus 0s plus 9 over here on the left-hand side. And so we know that these values of a plus c are equal to the coefficient on s squared, and so therefore a plus c is equal to 0. And then write same thing for this 3a plus b term. 3a plus b is also equal to 0. We have no terms of s on the left-hand side, right? No terms of s in our numerator. And so this is also equal to 0. And then 3b is equal to 9. So 3b is equal to 9. So right off the bat, we know that b is just equal to 3. And so then 3a plus 3 is equal to 0. A is equal to -1. And then c is equal to -a, and so c is equal to 1. And there we go, pretty simple. That's how we found our values of a, b, and c, and we're going to plug it into this partial fraction here. And so we will get -1 over s plus b, 3 over s squared, plus c, which is 1 over s plus 3. And so we have now transformed this original function that they gave us up here into something of 3 separate terms that now match the model within our lookup table of these 3 terms, right? 1 over s squared, and 1 over s plus a. And we know that if we go from f of s from the frequency domain back to the time domain, this is the inverse Laplace transform. And so 1 over s is u of t, 1 over s squared is t u of t, and 1 over s plus a is e to the negative a t u of t. And so we can go ahead and know that this term here, right, is just equal to negative u of t. And this second term here is just going to be equal to 3t u of t. And this last term here, right, 1 over s plus 3 is just going to be e to the negative at ut. And so that's just going to be e to the negative a 3t u of t. We can factor out this u of t here, and we will get -1 plus 3t plus e to the negative 3t times u of t is equal to our function, which is equal to the inverse Laplace of our original function of s. And this is ultimately our answer. And so, our answer. So if we go over to our answer choices, we will see that we have the correct answer right there. And so that's it. That's a very simple inverse Laplace question. And so just to review what we did here, they gave us some function of s, and they wanted us to inverse Laplace transform that. And so this function of s is within frequency domain, and it is the Laplace transform of some time domain expression. And so we're going to perform the inverse Laplace in order to get that time domain expression. And so what we did is we took our function, we did partial fraction decomposition, right? We took the terms in the denominator and we separated them out into 3 separate terms. And then from here, once we got this partial fraction decomposition, we went up to our lookup table and recognized that they were of these 3 forms, and that the inverse Laplace gave these 3 terms. We applied that in specifics, and we ended up with this as our final answer, as the inverse Laplace of 9 over s cubed plus 3s squared. And so that's it, and that's pretty straightforward. That's it. Okay, question 8. Find the Laplace transform of the inductor current for the RLC circuit below. Assume that I sub L of 0 is equal to 0 amps and V sub C of 0 is equal to 0 volts. Okay, what we have here is we have a 0 state response question. And what this question is asking us to do is find the inductor current in Laplace domain. So it wants us to find I sub L of t in terms of s, with s being our complex frequency. And so what we're going to do, because they have given us no initial conditions, is we're just going to transform this circuit here into its Laplace domain equivalent, and then we're going to set up a KVL expression since we are in series and just solve for the inductor current in terms of s, right? So I sub L of s, that's what we're trying to do. So let's do it. So this voltage source here, right, e to the negative 4t ut. If we look at our Laplace table, we have an a value of 4, and so it's just going to be 1 over s plus 4. And then we now need to transform these RLC components into their Laplace domain impedance equivalents. And so if you remember back to 2K1, it is the same concept. So the impedance of an inductor is equal to L times S, with S being our complex frequency, sigma plus j omega. And so in 2K1, we only use j omega because we were only using sinusoidal inputs. But now that we use S, which is sigma plus j omega with a real component, we can now use exponential inputs. And so the impedance for a capacitor is equal to 1 over C times S, right? So for an inductor, as frequency increases, as S goes up, our impedance goes up. As frequency increases across a capacitor, as our S goes up, the impedance goes down, right? That is just basic behavior of inductors and capacitors as frequency varies. And so then for a resistor, the impedance is independent of frequency, and so it's just equal to its R value. So let's apply that here, and we get L times S, which is 4S, and then 1 over C times S is 2 over S as the impedance value for that capacitor. Then this resistor value just becomes this. So now what we're going to do is we are going to set up a KVL loop, right, a Kirchhoff's voltage law loop, that the voltage of this exponential input is going to be dropped across all three of these elements. So, V in of S is equal to VL of S plus V sub C of S plus V sub R of S. And then we can use Ohm's law and say that these are equal to I sub L of S times our impedance value. Sub C of S times ZC plus I sub R of S times Z sub R. And we know that because we're in series, the current through all of these components is equal. So I sub C of S and I sub R of S is equal to I sub L of S, what we were trying to solve for. And so we can say that V in of S, which is 1 over S plus 4, is equal to our inductor current times the impedance value of that inductor, 4S, plus our capacitor current, which is equal to I sub L, what we're trying to solve for, times our impedance value of the capacitor, 2 over S, plus I sub L, times 1. And so then we can factor out this I sub L term here, and we'll get that 1 over S plus 4 is equal to I sub L of S, the current through our inductor in terms of Laplace domain, multiplied by 4S plus 2 over S plus 1. We're going to divide this value out, and we will get that 1 over S plus 4 times 4S plus 2 over S plus 1 is equal to I sub L of S. And so this is our answer. But when we go up to our answer choices, we do not see this answer represented in any of them. And so what we need to do is we need to change this real quick. And so if we look, we either have a term of 4S, we either have a term of 1 on top in order to get this denominator into that term. So what we're going to do here is we're going to multiply by S over 4, and if that doesn't get us into a term, then we'll multiply by 4 over S and hope that by multiplying by that, we're going to get this right. So this is, we're going to multiply S over 4 divided by S over 4. All right, this is just 1. So then this equals S over 4 divided by S plus 4 times S squared plus 2 over S becomes 1/2 plus S over 4. And there we go. This is our answer for our inductor current in Laplace domain. And when we go up to our answer choices, we have it right here. And so just to review what we did, they asked for our inductor current. We had 0 initial conditions, and so we just transitioned this circuit into its Laplace domain equivalent, right? We used our Laplace transform for the voltage source, and then we used what our impedance values are for inductors, capacitors, and resistors in Laplace domain, which is a throwback to 2K1, except for we're using S instead of j omega. We made this circuit. We set up a KVL expression. We solved for I sub L of S. It was equal to this, and then we multiplied by S over 4 in order to get it into our answer form, and we got F as the right answer. And so that's how we do it. Pretty straightforward. Let's go on to the next one before this thing dies. Okay, question 9. Find the transfer function of I sub of t for the circuit below. Okay, we have a transfer function question. In particular, they want us to find the transfer function of I sub of t, right? The inductor current within our circuit. So what's a transfer function? Well, it's H sub s, and H sub s is equal to our output divided by our input. And the way that we derive that expression for what a transfer function is that for any LTI system, the output of a system is equal to its impulse response convolved with whatever you input. And so when we Laplace transform that equation, we get our output in terms of S is equal to our impulse response Laplace transformed, which is our transfer function, right? Our transfer function is the Laplace transform of our impulse response. And convolution in Laplace is multiplication multiplied by whatever input function we have in Laplace domain. And when you divide x of s out, we get this equation. So that's what we're trying to do. And for this particular system, the transfer function h sub s is equal to our output, which is our inductor current, divided by our input, which is our input voltage. And so all that we're trying to do is solve that equation that I just wrote there. So how are we going to do that? Well, when we're solving transfer functions, we want to see kind of like what form it's in. And so in this case, it's equal to I over V. And I over V, right, by Ohm's law, is equal to 1 over the impedance, which is equal to the admittance. And so if we can get this expression over here in terms of I sub n over V sub n, we can just make that equal to the admittance of the particular circuit based on the input nodes. So in order to do that, first we need to transform our inductor current into an expression of I sub n. And the way that we're going to do that is we're going to perform current division, right? So the input current splits at these two branches. And so the current through the inductor is equal to, by current division, the impedance of the alternate branch, which is our resistor, divided by the sum of the impedances multiplied by I sub n of s. And so let's write, this is an impedance of 2, this is an impedance of 4s, right? The impedance of an inductor is equal to L times S, with S being our complex frequency. And so this is equal to 2 divided by 4s plus 2, I sub n of s. And so this is equal to 1 over 2s plus 1, I sub n of s. And so we can plug in this value of I sub L of s in terms of the input current into this equation in order to now have our transfer function equal to 1 over 2s plus 1 times our input current divided by our input voltage. And so, as I expressed earlier, this is equal to the admittance of the circuit based on the input nodes, right? I over V is equal to 1 over Z. That's equal to our input admittance. So all we need to do now is find the admittance of this circuit, not circle. So let's rewrite it. We have this resistor, and then we have the inductor and the resistor. And so let's find the impedance, which will be equal to 1 over yn. We can just flip it, right? The impedance is the reciprocal of admittance. This is 1, this is 4s, this is 2 in terms of their impedance components. So this is equal to our first resistor plus the impedance across these two nodes, right, of those two elements, which is just our product divided by our sum. So 4s times 2 divided by 4s plus 2. This simplifies out to 1 plus 8s divided by 4s plus 2. This simplifies to 1 plus 4s divided by 2s plus 1. We can write 1 as 2s plus 1 over 2s plus 1 plus 4s divided by 2s plus 1. This is equal to 6s plus 1 divided by 2s plus 1. And this is equal to the input impedance. And we want y sub n, which is equal to 1 over our input impedance. And so this is just 2s plus 1 over 6s plus 1. And this is equal to our input current divided by our input voltage. And so we can replace this expression here, and we will get that the transfer function is equal to 1 over 2s plus 1 times this value here, which is 2s plus 1 divided by 6s plus 1. These cancel, and this is equal to 1 over 6s plus 1. And if we go over to our answer choices, they want the coefficient of s to be 1, so we're going to multiply this by 1/6 over 1/6 in order to get it into the form that they'd like. And so ultimately, this is the answer. And when you go over to our answer choices, the correct answer is A. So just to review what we did here, sorry, this is the last question. What we did here is they wanted us to find the transfer function of the inductor current. And the transfer function is equal to the output divided by the input, right? The transfer function is the Laplace transform of our impulse response. And so therefore, it is equal to the output divided by our input, which is equal to the inductor current divided by our input voltage. And so then we got it in terms of I sub n and V sub n. That way we could plug in the input admittance. And the way we did that, we performed current division in order to get I sub L of S in terms of I sub n of S. We replaced it. And then we just found the impedance of the circuit based on the input nodes. And then once we did that, we found the input admittance because it's just the reciprocal. We plugged that value into here and we simplified, and this is the resulting transfer function of I sub L of S divided by V sub n of S, and that's our answer. I hope that makes sense, but anyways,